Good afternoon, everyone. So, yeah, I'm Craig Knott, and I'm an SRE at Atlassian. And as was just said, I'm going to speak to you about some server-to-cloud migrations, and basically how we managed to take advantage of stateless cloud services to improve the reliability and resiliency of our server products. So, quick show of hands. Who here is running some sort of monolithic application in the current data center or on some VMs? Yep. Cool. Who here is planning to move to public cloud or their own private cloud in the near future, or currently in the process of migrating? All right, excellent. So this will be useful for a few of you then. For many of you who are already familiar with running services in the cloud, there'll be a lot of content here which you'll already know. So just bear with me as I get through that. All right, so a bit about myself first. As an SRE at Atlassian, I've been able to experience our transition from a traditional core operations team to our currently and still rapidly growing SRE organization. And so in that time, I've been involved in at least half a dozen of our SRE teams. And then obviously, most importantly for this talk, I've built, planned, and executed multiple migrations of our enterprise server products from our own data centers into a cloud platform that I've created. A little about Atlassian. So who knows who Atlassian is? Brilliant. Don't need to explain this to you. If you haven't heard of Atlassian, you've probably heard of our products. We've got JIRA, Confluence, Bitbucket, and Trello are just a few of them. And so we have a strong history in server products, but we also have an extensive cloud offering. And obviously, with the cloud offering comes a fair bit of operational work. So every day, we've got more than 100 teams, around 600 core services, hundreds of changes happening every day across multiple products, and we have many, many customers. And so supporting those customers are our wonderful support staff. And behind that support team, there's another support team. And that's the customer support technology team. And so they build and maintain the tools that the support team uses every day. And so that's the customer support technology SRE team supporting the customer technology team. So basically, all the tools created by the customer support technology team have an SRE team to support them. And so at the time, the main things we were doing here is running JIRA Datacenter. Anyone run JIRA Datacenter? Cool. Confluence Datacenter? Yeah. And so I'm going to be using JIRA Datacenter today as a reference throughout this talk. So if you're familiar with that, that'll be good. Otherwise, a quick overview of JIRA Datacenter. JIRA is Atlassian's issue tracking and agile project management product. And JIRA Datacenter is the deployment option for that enterprise customers use to run JIRA on their own hardware. So important technical notes about JIRA Datacenter. It's a Java app. It requires a database. It can be run in a highly available clustered mode. And when running in a cluster, it requires a shared file system. So, story time. Where does it all begin? So back in the day, we're running our JIRA and Confluence data center, and we were on some of our own hardware, running on some VMs. And at that time, we had another team that actually looked after that platform, maintained everything, and looked after the VMs. And everything was sort of OK to an extent. And then one day, this happened. So our VM platform team came to us, and they said, there was a decision made, obviously by people who get paid way more than me to make these sorts of decisions. And they decided to wind down our VM platform, as well as the team supporting it, and then reassign them to new work. So what did this mean for us? Well, first, we had to take ownership and support the VM layer now upwards. And second, the platform was going away, so we had to come up with a plan to migrate our products somewhere else. As there was no immediate migration path, we decided to investigate a few solutions to move away from server management to image management. And the goal with this was to make our lives easier as the new service owners. This is what it looked like beforehand. So a little bit more context. We'll go through each of the layers of how we're running our JIRA Datacenter is our clustered app in this case. So a few important notes here. The underlying VM for each of these components was managed by our VM platform team. and now it's managed by us. Services running on top of the VM could be owned and managed by one team, or there could be multiple teams all using it and sharing it at the same time. So that was pretty strange, but we'll go through each thing. So starting at the top, HA proxy, if anyone's familiar with that, we had a little bit unusual configuration here. So it was shared across every product running on our VM platform. All inbound traffic went through this HA proxy. And I'm not going to try and explain HA proxy or pretend to be an expert here, but I am an expert at having other teams make changes which impact my service. And it happens way more frequently when you're sharing a load balancer config. Moving on to the next layer, is a web server layer. It's bound one-to-one to the app server. And this meant that if either the web or the application server is down, that whole part of the cluster would be down and removed from the load balancer. The app layer, so we're talking about JIRA Datacenter here. It's clustered, so we have 2 nodes here. Upgrades are difficult, and we were doing a lot of individual human changes on here. So any config changes, you might want to change the JVM parameters. There'd be a lot of SSHing in, making changes. And finally, the persistence layer. So like I said before, JIRA requires a database and a shared file server. And in this case, we have to build and manage the database and file server, so it's not just out of the box, you just get it. So what's the problem? Well, there's 3 major issues with this configuration that I came up with here. So the team responsible for running the services, like I said, had to SSH in quite often to investigate problems, make changes, or install updates. And so this would lead to inconsistencies across the servers. Unfortunately, we aren't robots. We do make mistakes. So most likely of this is a change we made on one server and then not applied to the other. And the result of these inconsistencies generally surfaced in product instability, and that led to outages. So what we're going to do? Well, we were just getting kicked off our platform, so we're going to try and migrate to cloud services. So how are we going to do that? So at Atlassian, we actually already have an internal platform that we could have tried to use. Unfortunately, it's really only for supporting microservices. And we're trying to use this monolithic application, which has a lot of state in it. So that wasn't going to work. So we're going to build our own platform. We had to choose a cloud provider, and the rest of Atlassian's using AWS, so it seemed natural we'd use AWS. And then finally, I was thinking, what's the benefit of this cloud stuff? So what are we going to get by moving to the cloud? We're going to get managed services. We're going to get scalability and potential free resiliency wins. OK. So after deciding that we're going to use AWS, we had to take a step back and just think about the different components that were required and that we thought were particularly important for our new platform. The first thing is we wanted it to be easy for developers and non-developers to understand our tooling, use it, and improve upon. We needed a way to be able to audit any changes, and we wanted to manage images rather than servers. So how are we going to do that? Well, we'll break it down into 5 layers. So everything starts with tooling. After we've selected the right set of tools, we're going to move on to image creation, and then orchestrate our infrastructure to run the images. Then we're going to look at our CICD pipeline, and then finally ensure we've created and enabled all the necessary monitors and dashboards. All right, so first, let's talk about tooling. Our tooling needed to support the other 4 layers of our platform, but most importantly, when getting started, the image and orchestration layers, as this is where the products are actually deployed and run. So what tools did we need? Orchestration, image creation, and configuration. So I've mentioned it a few times, but just to clarify what I mean when I say orchestration, if there's anyone that's unsure, I'm referring to the ability to configure, deploy, and manage cloud services in an automated and reproducible way. So there's 2 prime candidates for our orchestration tooling. We're looking at CloudFormation, because we're on AWS, and Terraform. So both CloudFormation and Terraform can be used to manage our AWS infrastructure as code, which is great. And there's a few differences, though, so let's go over a couple of them really quickly. So some of the pros of CloudFormation is built by AWS, so it works really well if you're using AWS. Doesn't work so well if you're trying to use another cloud provider. It also has great support for all of AWS's services, and generally, it'll support newly released services before Terraform. We also found its state management was a bit easier to configure than Terraform's, in the fact that you didn't really have to do anything to configure it. But Terraform also had a lot of pros. So Terraform's open source. So if there's a feature missing, or you need to make a change to something, you can work with the rest of the community to implement whatever you needed, which we actually had to do during this process. It also supports multiple cloud providers and can be used for other non-cloud provider services, which I'll get to later. When it comes to modularization, we really preferred Terraform's method of managing self-contained configurations as a group over CloudFormation's has a multiple different approaches that you can use. And so we prefer Terraform for that. And lastly, we found Terraform's change verification was a bit more detailed when running a plan than CloudFormation, and we really like that too. So we decided to go ahead and use Terraform. So after choosing Terraform, we had to look at image creation tooling. And obviously, we're already using Terraform, which is created by HashiCorp. So the choice for image creation was pretty straightforward, and we decided to use Packer. So quick overview of Packer. It's an open source tool for creating identical machine images. You can use it to create images across multiple platforms from a single source. A machine image is a static unit that contains a pre-configured operating system and install software, and we can use it to quickly launch new machines. In our case, so we just configured a machine with some JIRA running in it. Super easy. So that's Packer. And then lastly, we had to decide on a config management tool. We had been using a monolithic, like gigantic Puppet repo across the entire company, but most of our SREs were moving towards using Ansible. And so we decided we would also head towards Ansible for configuration management. And this also tied in nicely with Packer because you need config management along with Packer, which I'll get to in a minute. OK, that's tooling. So after we've decided on our tooling, we moved ahead to creating our AMIs. And if you don't know what AMIs are, that's AWS's machine images. As I mentioned before, we're using Packer. This is what Packer looks like. It's super simple. It's a JSON file, and it also uses a config management tool for provisioning any required resources. There's heaps more detail you can provide. It's all available on Packer.io. If you want to base your AMI for an existing image, if you want to attach any additional volumes, you can change the root device side. If you want to add any tags, this can all be done in this JSON file here. The important part is the provisioners here. So you can't just have the builders. You have to define a provisioner. And this is where the Ansible comes in. So you create a playbook, which will have some roles. And basically, Packer will spin up a base image, and then run Ansible to implement any of the changes you require, and then save that image for you to use later on. You can also provide more detail than is provided here. Obviously, it's all available online. The other provisioners may have different variables, variable requirements in the config file. All right, so that's creating an image. And now, we could actually easily configure and run this manually. Now that we've created an image, we could build a very similar setup to our original architecture. So that would have like HA proxy at the top would now map to having an ALB or an ELB from AWS. We don't need the web layer anymore. We can just route straight through the application layer, and that would just be our image running on EC2 in some sort of auto-scaling group. And then our persistence layer, we've now got, instead of running our own database, we could just create a Postgres on RDS. And instead of having our NFS that we had to manually run, we could move to EFS. But configuring and running this manually wasn't going to be good enough. So it would leave us in a similar situation as before with many manual changes. We wouldn't have any peer review, and there'd be high potential for error. So although we at least removed some potential of a human error by creating an image, there's still a lot of error that could happen on the orchestration part here. So let's look at how we can fix that. So as I mentioned earlier, we're using Terraform for orchestration. And anyone who's worked with AWS will realize the first thing you need to do is create some VPCs. In our case, we needed 3, 1 for dev, staging, and production. Not only is this good practice, we already had a few experiences in our previous platform with many problems occurring from having a poorly managed pre-production environment. So we wanted to get this right from the start. It was challenging to keep our pre-production environment in sync and actually perform any pre-prod testing. We also decided to create an additional VPC to provide a layer of abstraction from the company. And the main role here was to control access to the other VPCs through the use of Bastion hosts. So how does that look in Terraform? So I'm not going to deep dive into the config for each resource in Terraform, but like Packer, it's fairly simple, both logically and syntactically. And there's plenty of documentation to help guide you along the process. What I will do is go over how we structured our project and took advantage of Terraform's modularization to simplify and remove duplicate config. So at the top level, we separated it into environments and modules. Environments then contained a folder for each of our environments, and modules contained a folder for each of our modules. And then diving into the modules, this is what could be going on in some modules. So like I mentioned before, module is just a group of self-contained Terraform configuration. And in this case, it's just a collection of Terraform files. And the main parts here, which I care about explaining, is the inputs and outputs. So the inputs are variables, and outputs are outputs. And these are just Terraform resources. And the rest of it can configure anything you want. Generally, I put them in main or separated it by relevant naming. Jumping into the environments, this is where we'd have our separate products. So product A could be JIRA. Product B could be Confluence. And then the only difference between each of the products was setting in each of the environments, for the products, it's just the variables. So you just need the variables file and then to initialize the module. And that will look something like this. So one of the variables in the VPC module might be some VPC CIDR, and then you would initialize the VPC module. Once again, pretty straightforward stuff. So by using Terraform, we're able to set up our VPCs as well as configure our product stack. And now we can make peer-reviewed changes and maintain an audit log, which was the second part that we wanted to check off. And once again, just how it compares to the old architecture. OK, so while all that was in progress, we were also working on our CICD pipeline. So at the time, Bitbucket Pipelines was just coming out. So we thought, let's try that out. Turns out it was super easy to configure. All you need to do is create a simple YAML file with some basic configuration. You could use a bash script or a Python script, whatever you want, to execute your build and deploy. If we hadn't used pipelines at the time, we would have just been able to do the same thing on Bamboo. So if we're looking at our Terraform pipeline, it all starts with identifying a change. So we found something that needs to change. We're going to raise a ticket, make the change, raise a PR, and get it reviewed. Once it's been reviewed, reviewed, approved, merged, pipelines will kick off a build automatically and then immediately start deploying to our development environment. And after a successful deploy to dev, we configured pipelines to allow a one-click promotion to deploy to staging and then production. So we could deploy to dev, test it out, check that it's all working as expected, do some quick in-app testing, and then deploy to staging, and then production. Pretty standard. We can do the same thing with Packer to make changes to our AMIs, but the only difference here is that after building a new AMI, we would have to redeploy Terraform. And the reason we need to do this is because Terraform would then pick up the newly created image and then relaunch the instances with that. The final thing that we needed to consider before we could actually begin the migration, was our monitoring and alerting. So monitoring may seem confusing. Everyone does monitoring a little bit differently. But at Atlassian, we're using Datadog for almost everything. And there is a really neat CloudWatch to Datadog integration. And so being on AWS, we just took advantage of that. In addition to that, we are also running agents on each of our EC2 instances. And we use that to collect additional metrics about the running products, particularly inside the JVM. So this platform wasn't going to just be running 1 or 2 products. There was going to be more and more products being added, and there have been over time. So what are some of the realities of a growing business? As you're adding more products to a platform, how do we ensure we can scale our monitoring? So as we add more services, your number of monitors and dashboards is going to keep growing. So how much time does this mean that you're actually spending building and maintaining monitors? Well, it's probably going up, but you would like it to go down. So how can we do that? You remember Terraform? Turns out we can use that with Datadog as well. So Terraform has a great Datadog provider, and we've been using that for the last year or two to configure and manage all our monitors and dashboards. And so this is what happens when we use that. So now we can create reusable modules in Terraform and apply them to our new services. So this means that by having a small overhead at the start, we can provide long-term benefits when it came to the amount of time that would be spent maintaining monitors as we scaled up and introduced new services. And just like before, we can do the same thing with Bitbucket pipelines to deploy the Terraform changes for Datadog. OK, migrations time. So at this point, we're able to create, deploy, and run our products on the new platform. But we have no data. So the next step is migrate our data from the old VM platform to our new AWS platform. And so migrations can be a bit tricky and vary wildly from case to case. So this might not apply to you directly. So I'm going to try and give some broad steps that we took when migrating, and then some guidelines that are good to follow that we've discovered along the way about planning and executing the migrations. So before we even began to migrate, there was a lot of planning involved and discussion with the stakeholders to ensure that everyone's on the same page and understood what was going to happen, when it was going to happen, how long it's going to take, all of that. And so now, how we did it, basically, leading up to the migration. So in the days before the migration, we would pre-configure JIRA on our new platform, ensure that it was able to be started on a single container or could cluster up across 2 or more. But at this point, we have no data, OK? And the second step was then to migrate the data. Straightforward. We had 2, like mentioned before, 2 sources of data in our persistence layer, RDS and EFS that we're migrating to, so Postgres and NFS. And then finally, once we've migrated the data, you're going to check that it's successful. And then if it was, you're going to cut over DNS and just serve traffic to the new platform. If it wasn't, you're going to abort and keep running on the old platform. One of the less obvious things to consider was whether or not you could put the original install into a read-only mode. And so this would then reduce any sort of, or remove any sort of data loss that could happen during the actual migration. A bit tricky for JIRA, but works nicely in our instance when we're using Confluence. A couple of the failures that we had during our migration, before I get into some tips. So we performed a lot of migrations. And so these are just a couple that happened early on as we were trying to figure out what's the best way to do this. So one of the earlier migrations, we actually forgot to transfer DNS ownership from the platform team to us. So we got through migrating all the data, and we're like, yay, it's all happy and good. Let's cut over DNS. And we can't. So we had to roll back. We did that next week, and it all worked fine. Another instance we ran into trouble was during the NFS to EFS migration. we actually mucked up the file permissions. So this was due to lack of testing and automation. So once we started up JIRA on the new instance, we couldn't see any images. Everything was owned by root. So the fix for that, obviously, is just we ran a churn across the EFS to fix that. But that was a good couple of hours of no images or attachments working. OK, so that was a couple fails. Here's a couple of migrations planning takeaways. So there's a lot of text, but no one likes a project that gets delayed over and over. So make sure you plan accordingly. And remember, no plan will ever be perfect. So don't spend all your time planning and then never actually get to migrating. Because your stakeholders probably won't like that either. Speaking of stakeholders, get them involved early. You want to discuss and make decisions around things like whether there'll be downtime. If so, how long will the downtime be? Do we need to minimize it? Is it worth the effort? How do we notify our customers? And then document everything. You want to ensure that any member of your team could pick up the migration plan, understand it, and execute it. And I say any member of your team because I had an SRE who I was working with who wanted to document so much that any member of any team could come along and do the migration, which isn't going to happen. Please, no other team come and do my migrations. OK, so you also want to make sure that anything that can be done before the migration gets done. So like I said before, we pre-configured our new environment as much as we could, right up to the point that we had JIRA running with no data. And so this is really important if you're going to be taking some sort of outage and you're trying to minimize it. If you can take the site down for 2 weeks, then you obviously don't have to care so much. You also want to make sure you consider how you're transferring the data. So make sure you're protecting your customers' data. You don't want it to accidentally get exfiltrated during the process. Last couple things, automate everything. So like I said, we mucked up early on and didn't automate as much as we could. And so if you find yourself having to manually connect to servers, run some bash commands on the fly during the migration, you should consider scripting that beforehand. Don't be afraid to abort. We had to abort in one of a couple of our migrations. So if something doesn't go as planned, you can always try again another day, the next week, whenever. At least I hope you can. And finally, test, test, test. I can't stress this enough. This is why you have the pre-production environments. You want to test your migration plan thoroughly multiple times in the lead up to ensure that you're as comfortable as you can possibly be with the entire process. All right, cool. We did it. We successfully built our platform. And now we can support our products, migrate into AWS. So I just want to quickly mention a couple of the few wins we got immediately from the migration. So like I said earlier, managed services. So we now have RDS, EFS, load balancer. Those are 3 things we don't have to look after anymore. In our previous platform, we were maintaining a load balancer, maintaining our own Postgres, maintaining our own NFS server. Now we also get some free AZ failure and single node resiliency wins. So running on our EC2 instances, we don't particularly care about a lot of the state that is in that instance. We create other images in such a way that they can easily be terminated and then respun up, and they'll just rejoin the cluster. So we're really happy with that. But there are a few improvements that we can make. So we thought, great. How can we make this even better? And remembered that we have the advantage, having the advantage of already using some cloud services. We can continue building on top of this. And so we can continue to build new services or utilize AWS's managed services to make further resiliency improvements. And honestly, this is probably like the nicest hack you can do when you're trying to run a product which isn't actually suited to run on stateless cloud services. In order to do this, we had a look at the core capabilities of JIRA. And so these are the features that we thought were most important to our customers' everyday use. Ticket creation and updating tickets. And so in the event of some sort of degradation or outage, no one could create any more tickets or update them. And so we thought, I wonder if there would be possible to have an alternative. And it turned out there was. if I can click. There we are. And so we could take parts of the product and break them down into microservices if you are a developer on the product, or we can wrap parts of the API to achieve a similar solution. And so our users now hit another service instead of the JIRA's typical ticket creation service. So we wrap the ticket creation API using AWS's services to create a single-page app, runs on CloudFront using API Gateway and Lambdas and SQS. Requests come in, they get queued up, and we try to submit them to the API. If it fails, put them back in the queue, and we'll try again later. And so this meant when JIRA's down, our users can still submit requests. And so that was pretty neat, and something that you can do when you're on AWS. So just to recap quickly, today I spoke to you about making the decision to migrate our products to AWS. We determined the core requirements of the new platform, which is we want it to be easy for developers, non-developers to understand, use, and improve upon. And we needed a way to audit any changes, and we wanted to manage images rather than servers. We spoke about selecting the appropriate tools to get the job done, and we chose Terraform, Packer, and Ansible for our orchestration, image creation, and configuration management, along with Bitbucket pipelines for our CICD. I covered some of the basics of Packer and Terraform, as well as how our team decided to structure each of our projects. I also briefly discussed how we used pipelines and how we used Terraform to manage and configure our Datadog monitors and dashboards for optimal future scaling. In the end, we were able to successfully migrate from our original state to AWS. So finally, I want to leave you with a few key takeaways. So by using cloud services, like I said before, we immediately got the benefits of not having to manage things like RDS and EFS. We got immediate resiliency and scaling wins, and we were able to improve the way we built and ran our platform through the use of quality tooling. We learned a lot about migrating data, planning, and executing migrations. And we also got the opportunity to utilize more cloud services to iterate and improve on our service. All right, so that comes to the end of the talk. If there's any questions, I'm happy to take Q&A. Otherwise, thanks.
Hi, great talk, thank you. Can you please elaborate a little bit on testing behind Terraform pull request and maybe Packer image building, and maybe using some test infrastructure, testing frameworks like server spec and spec test kitchen? Thanks.
Sure. So for checking before we release changes to Packer or Terraform, some of the reasons why we chose Terraform over CloudFormation is because it has a much more detailed plan. And so that was the primary method of actually checking that things were going to work out fine. So in part of the build, before it would deploy to development, in our branch builds, it would run a plan and give us an output of exactly what it's going to do. And so this was our method of verifying what was going to actually happen. This isn't as much like writing code that you're going to write tests for new changes. It's really, the onus was really on the people making the changes and the team running the platform to ensure that things were happening as expected.
I actually have a thing I'm curious about. So
sure.
You said that you wrapped your API to, instead of directly instantiating the requests, to add them to a queue and then retry them if they're not able to be run. So my question is, that then makes the request asynchronous between the user and actually affecting your backend service. Then that means that if an error occurs applying the change, it's harder to feed that back to the person who made the request immediately. So how have you dealt with that problem?
Okay, I'm not sure if we're having errors because creating this in such a way that it only speaks to the API for ticket creation. We're putting in the exact requirements to the API every time. The only errors we're getting are those that we expected when the whole application is down for whatever reason.
Okay, so no way you can end up with an invalid request.
No, so everything is obviously validated enough on input.
Cool. Any more questions? No more questions? Cool.
Awesome.
Okay.
Thanks, everyone.
Thank you very much.